The goal of this video is to teach you what a derivative is. This is a concept that you'll learn in the beginning of calculus, typically Calculus 1 or AP Calculus, something like that. And a lot of people have trouble with this concept, especially since it's, dealing with infinities and really small numbers and stuff like that, and a lot of it doesn't really make sense. So I'm going to try to make sense of that for you today. And so yeah, let's just begin. So the derivative is just basically a way to generalize the concept of slope. Alright, so I can basically put here, down here. So this is basically slope. Okay, and what we're going to be doing is we can consider some function here. And let me just start off with a linear function, and I'll just draw it something like that. So that's our linear function, and I'll just call that f. And if we want to find the slope, well, we can choose any 2 points. Let's say this point, which I'll call point 1, and then this point, which I'll call point 2. And each of these has an x and a y coordinate. So this one has the coordinates x1, comma y1, and then this one has x2, comma y2. Okay? And so from here, the way we would calculate slope is we would take the difference in the y divided by the difference in the x. Okay? So this is delta y, and this is delta x. Right? And so what we do, so let me write this explicitly. We take, so the slope, which is usually m for linear functions like y equals mx plus b or whatever. So m is just, so it's going to be the difference in the y divided by the difference in the x. Or in other words, we can think y2 minus y1, that's our difference in the y's, and then divide that by the difference in the x's, so x2 minus x1. Okay, this is just stuff from algebra. If you're on this video, I expect that you already know this and you know how to work with this, you're comfortable with it, but now we're going to be extending it to not just linear functions, not just straight lines, but to any other curve. So let me take a function here, something like that, okay? This is our new function, and I call this f. I'll call this, I'll also call this f. They're just different functions, but it's usually easy to just use the letter f. So another way to phrase this is whenever we're dealing with the y coordinates, we can think of these as f of x's, right? So this, and I can do this in blue, so this we can think of y1 as f of x1. So the way to think about that is you have your x coordinate, which is something like that, maybe that's like 1 or something, and then you evaluate that function at that particular x value. So you're taking f and you're evaluating it at x1, and it gives you y1. Okay, so similarly, we can think of this as f of x2. Alright, and so with that in mind, we can write that m is f of x2 minus f of x1 divided by x2 minus x1. Okay, that's another way we can think of this in a more functional view, right? So this is our slope, and like I said, we can just choose any 2 points anywhere on this interval and we'll be fine, or on the line and we'll be fine. So I could have chosen like this point and that point or something, or maybe this point and this point over here. It would all give me the same answer because we have a constant slope. Our function is increasing at the same rate throughout the entire domain. Here, it's clear that it's not increasing at the same rate. In fact, in some places our function is decreasing, it's going down. Here it's increasing pretty steeply, here it's about 0, and you can notice that the slope is going to be changing. So we cannot just choose any 2 points, get our slope and have the same answer. If I chose this point and this point, I would get a different slope than if I chose this point and this point here, right? So we have to think in a different way. So the problem is you can see that the slope at individual points is different from each other, right? This, like I said, this is about 0 here, this is increasing, it's some big positive number. But the problem is, whenever we talk about slope, we have to have two coordinates. We have to have x1, y1, and x2, y2. Here we don't have that. We, if we're trying to calculate the slope at one point, how does it make sense to use 2 points for that? That doesn't make sense. What we're going to be doing is using a limit. So I can write this in red for you guys. So I do expect you guys to understand the concept of a limit. And that's because it's going to be used in the definition of the derivative. So let me consider, let's take some point here, and let me call that, I don't know, we'll say x comma f of x, okay? And so now we want to find the slope of f at this point here, x comma f of x. But remember, we need 2 points, so where is that second point going to come in? Well, what we can do is we can take another point over here, and so there are 2 ways about going about this. I think I'll save the second way for another video, but here's one that's usually showed first, and that is taking, so we can think of here, we have this x, this is x, and then what we're going to do is we're going to go down here and say this is x plus h. So that x coordinate is x plus h, where this difference here is h. So h just represents the difference between the 2 x values, okay? So this is x and this is x plus h, so that means, so we know part of our coordinate here, so our x coordinate is x plus h for our red point, and what's our y coordinate going to be? Well, it's going to be the function f evaluated at x plus h. So it's going to be f of x plus h. Okay, so here we have our 2 points. We have x comma f of x, and then we have x plus h comma f of x plus h, where again that h is that difference in the x values. Okay, so now we have 2 points. Let's do the actual slope computation. So I'm going to again call this m, and what I'm going to say is it's going to be, well, let's use this as like our point, I'll call this point 1 and this is point 2 here. So we're going to start with f of x plus h. This is the difference in the x's, or in the y's. So f of x plus h minus f of x divided by now the difference in the x's, which is x plus h minus x. So we have x plus h minus x. Notice how we have x minus x, so that can go away. So let me just do that. And so now we're just left with h on the bottom, and that's it. Okay, but what that measures is this slope, right? It measures the slope between those 2 points. That's not the slope at this point, right? That's the slope between those 2 points. That's not what we're trying to find. What we want is the slope at this point. So what we do is we take h and make it close to 0, right? So as h goes to 0, so that difference in the x's goes to 0, this point here, this x value here, moves closer to the real x value that we're trying to actually find, and as a result, the function also moves down, and as a final result, because the x value is moving this way and the y value is moving that way, then the function is moving here, and so it ends up at that point. So we basically move this point down to here using a limit. And I pretty much spelled out what the limit is going to be. So here's what we have. So we're going to take that same thing that I wrote up here, and actually one important note is this is usually called the difference quotient. So this is the difference quotient, and so what we do with the difference quotient is we take the limit as h approaches 0, and we call this f prime of x. Okay, f prime of x is the derivative of f of x, right? And this is not a 1 that's a prime symbol, that's an apostrophe. That looks a little better. But yeah, so this is f prime of x. This is the derivative of f at a point x, which, you know, right now it's kind of just x, it's just a variable, but we could plug in a number. So we could say we want to find f prime of 5. So the derivative of f of x at the point 5, okay? And so there are different ways of doing that. So obviously you have to know how to compute a limit, the different limit strategies, for techniques for computation, stuff like that. And then once you do that, you can actually, you can leave it as is, as the function, or you can then plug in a number. So if we plug in a number, then we get a numerical answer. We get like, okay, the slope at this point is this. This looks like maybe, let's say it's about 10. Like the slope at this point here is 10, okay? Or we could keep it general and say f prime of x. So for any x, it's going to output a function, right? So because if we want to find the derivative of this entire function over its entire domain, then it's going to give us a function because the difference, or the slope at every point changes. So it's variable, so it's a function. So I know that's a lot to process, but pretty much this is the idea of a derivative. I do want to add one more thing. So this, as we know, is our derivative. And what it tells us is that if we plug in a point, and let's say we plug in the point x equals a, or let's just use a number, let's say x equals 5. So if we want to find the derivative at x equals 5, and we can maybe pretend that that is 5, then we can just plug in all of these and all of these. And so the h still stays there, right? So we still have to work with the limits with h. And obviously the way we would do this is actually by knowing what f is. We have to know that in the first place. But basically, what this limit does is it narrows the point down so it gets closer and closer to the actual value here. And it's not, their difference is not going to be equal to 0, it's just going to be really close to 0. So the 2 points will be very close together. They're not going to be exactly the same point, because then otherwise, if the difference is 0, then we're dividing by 0, and that's never a good thing. So we're not, the 2 points get really close to each other, but they're never actually equal to each other. And so what this does is it turns an approximation, which we did here, and it, you know, with that difference getting smaller and smaller, the approximation becomes more and more accurate until the points are so close together that the approximation becomes exact. There is also another similar approach to finding a very similar definition, so I'll leave that for another video, but I hope you guys enjoyed this one. Thank you so much for watching, and I'll see you in the next video. Bye guys!